Hi, everybody. Thank you for joining. Today's masterclass is Insulation and Ventilation, a deep dive. I'm Tiffany Pang, and I'm a junior consultant from Turner & Townsend. We are joined today by Kenny Lampert, a senior consultant from Turner & Townsend. This is a retrofit information support and expertise event, which is fully funded by the Department of Energy Security and Net Zero, delivered by Turner & Townsend. Thank you everyone for joining, and I will hand it over to Kenny to start today's presentation.
Okay, thank you very much, Tiffany. Yes, so today we'll be doing a masterclass on insulation and ventilation. So we recently ran a session a few months ago, which was just an introduction through insulation and ventilation. So the purpose of this session today is to go into a little bit more detail with regards to the insulation products that are available and are used through retrofit, and go into a bit more detail about ventilation and how these two topics intertwine and the importance of addressing both issues in retrofit. So quick skim through the agenda. So we'll start off by looking at why we need insulation and ventilation and the importance of both of these topics. And then we'll run through various different types of insulation. So we'll look at wall insulation, roof insulation, and floor insulation products. And we'll look at some good examples of these products being used in retrofit. And then we'll touch on air tightness and ventilation. And again, the requirements within retrofit standards for air tightness and ventilation. Okay, so why do we need insulation and ventilation? So older homes are typically very energy inefficient. So it wasn't until about the 1970s in the UK that insulation was introduced into the building regulations. So any homes built before the 1970s, it's unlikely it will have insulation unless it's being retrofitted. So obviously this is such a significant number of the UK's building stock, and therefore if we want to tackle the fuel crisis and reduce moisture and condensation, insulation can help reduce both of these impacts. And the most common impact in uninsulated homes is poor quality ventilation. So we can see here from the most recent data coming out of Social Housing Fund is by far solid wall insulation, loft insulation and cavity wall insulation are the most common energy efficient measures, with windows and doors also accounting for the most impacts. You can see there, I think in wave 2.2, 25% of homes receive lost insulation, and likewise solid wall insulation has quite a significant impact, with heating and PV so less so, but the most common areas energy efficient measures over Social Housing Fund is insulation. Likewise, under HUG, loft insulation is one of the most common energy efficient measures. Solar PV counts for the most common measure, but even under this particular government funded strategy, loft insulation and other installations are key features. So how is insulation measured in retrofit? So a common term that people may have come across when going through retrofit strategies is U values and thermal conductivity. So a U value measure is how effective a building element, such as a wall, roof, or window, insulates against heat loss or gain. So the U value is expressed in watts per square meter per Kelvin and indicates the rate of heat transfer through 1 square meter of the material for every degree of temperature difference. So a very sort of simplistic example of what we mean here is shown on the image on the right hand side. So you can see there a high U value would be just for a solid wall construction, but if you were to reduce your U value, so in this scenario the lower the number the better, adding insulation obviously reduces that particular value. Thermal conductivity is a physical property that describes how well a material conducts heat. So not an element like a wall, a roof, or a floor. It is the conductivity of a specific material. It is a key factor in determining how insulating or heat conductive material is. And thermal conductivity is measured in watts per meter Kelvin. So you'll often see various different insulation products have these metrics shown in terms of how they thermally perform, and we'll discuss a lot of those products today in this session. Before we do that, we'll just go a history of U values in the UK. So as I mentioned Previously, it wasn't until around the 1970s in the UK that we started to see insulation products in our homes. So around 1976, a typical wall U value had a U value of 1. And then as we go through the years and building regulations become more and more stringent, those U values drop more and more to around 1990. You can see there we have U values around 0.45 for walls. Around the 2000s, there's a focus on whole building energy performance. So that's when we start seeing requirements for not just the walls, but for floors and windows and ceiling insulation. And over time, that has come to the point where we have around 2019 U values of around 0.18, and those are continuing to become more and more stringent as we try and achieve our net zero goals. So, as I mentioned before, the vast majority of the buildings in the UK were built before the 1970s, and therefore it is unlikely that most homes will actually have insulation in their walls. Common that we'll see insulation in the roof, that's been a common feature for quite some time, but the walls and floors and potentially the windows as well, there's been quite a long period of time before they've had any insulation installed at all. So first of all, we'll look at external wall insulation. So we have examples here of mineral wool, so a very common insulative material used in retrofit. And these are man-made insulated materials with wool-like fibers spun from molten organic material, such as rocks and ceramics. And you can see here on the image on the right-hand side here, this is an example of how this could be used in a retrofit with solid wall construction. So you've got a solid wall, and then you'll have an existing plaster, or perhaps there's been a polish coat installed to even out the wall. And then typically you'll see a timber frame that's then fixed to the wall, and then mineral wool. It's a semi-rigid mineral wool that'd be cut into shape to fit between those battens. And then you'll then finish that wall construction with plasterboard. These thermal conductivities can vary between 0.032 and 0.044, and therefore obviously the lower the number, the better it is in terms of thermal efficiency. So those will tend to be the more expensive products, but there is quite a wide range of materials that can be used there. So typical costs are around 10 to 15 pounds per meter squared. And as I say, these are quite versatile products, so they can be used in any wall type and can also be used in roofing as well and flooring. Another common material is rigid PIR insulation. So these have very high performance and a thin profile. So you can see here in this table, we have thermal conductivities of 0.018 to 0.023. So it can be it's almost twice as good as your mineral wool. However, these products are more expensive and they're not always suited for all buildings and all retrofit projects, simply because should moisture get into the construction, these materials aren't always very good at then releasing that moisture that's built within the construction. So it can be quite a high risk and not always recommended on heritage buildings or any buildings, anything like that. But again, they can be used on internal walls, cavity systems. We've got a couple of examples again in retrofit here. So we've got another scenario where we have a solid wall construction, again, some existing plaster or a new polish coat to even out the wall, and then that insulation back plasterboard, which will usually have an integral vapor control membrane on the inside, fixed to the wall plaster, be it adhesives or on dabs, and then finished with skirting. Sometimes you may put a timber frame on there as well, just again to reduce the risk of moisture buildup and condensation through the construction. So sometimes that's a common scenario as well. Again, one of the challenges with this type of construction, certainly internal wall construction in general, is it will obviously reduce the room sizes and might require changes to skirting boards and plug socket locations and things like that. And obviously it can be quite a disruptive thing to do during a retrofit project. So it's not always common that people will use internal wall insulation, but those options are there. In addition, we have expanded polystyrene. So again, very similar to PIR insulation in the sense that it's a rigid board. But these have a good value for money. They're cheaper than a typical PIR board, and they offer moderate thermal performance. So you can see there again on the thermal conductivity for this particular product, you're talking around 0.030 to 0.038, which is whereas the PIR at best can be 0.018. So it is a better product, the PIR, in terms of thermal conductivity, but it might not always be the most suitable product. So you can see that sometimes people will use EPS insulation purely just because of costs as well. But it might be the case that if you're trying to achieve a certain U value, or you're trying to achieve a certain EPC rating, it may be the case that you'll need a thicker insulation product here to achieve the same U value. So it's one of those things you need to weigh up in terms of the cost analysis and the benefits of both scenarios. But EPS can also be used in blown insulation. So this is this is an external wall insulation. So rather than internal board, it'll be on the external skin of the envelope. Now this is quite a common solution, and we saw on that table at the beginning there that solid wall insulation was one of the most common energy efficient measure types. So it's quite a good opportunity to use these products again because it's less invasive in terms of the impact it has on the resident and the existing room layouts and room sizes. But it does come with its own challenges, and there are considerations that you need to consider. So it's only really suitable for when the solid wall homes. So again, you need to make sure that you've done your analysis during your retrofit assessment and make sure that you have a solid wall construction, and therefore you'll be able to specify a product like this. But it's not always straightforward. Some buildings have listed consent, or they're in conservation areas, so it might not always be possible to get these products approved. And another key consideration is to ensure that any existing walls are repaired from any damages, because often this can lead to cold spots and moisture ingress through the construction if the wall hasn't been repaired before this insulation is added onto the external skin. But again, as I mentioned here, it is one of the most common insulation products used in retrofit. But it doesn't always have to be an external wall insulation. It can also be used in blown insulation. So this is again, and around the 1970s is when cavity wall construction started to be, around the 1920s, cavity wall construction was common in the UK, but they weren't always obviously filled with insulation until around the 70s. So EPS blown insulation can be used, which uses small polystyrene beads that are injected into the cavity between the inner and outer walls of the building. Blown cavity wall insulation is a cheaper alternative to that of solid wall insulation, but can only be installed when there is a cavity of at least 50 millimeters. It can be used on cavities smaller, but in terms of cost effectiveness, a cavity of at least 50 mil is recommended by most manufacturers. If the cavity is not suitable, so it's already damp or poorly ventilated or exposed to driving rain, insulation can trap moisture. So again, it's really important to do a survey and ensure that the products can be used on this particular wall construction. And if there are any repairs that are required, that they're done before this product is installed. Separate to this, we also have natural insulation products. So these aren't common on a lot of retrofit projects in my experience, but they are available, and they are available for people to use. And again, in a scenario where you've got perhaps heritage homes or buildings in conservation areas, these are the sort of products that are often recommended in order to help protect those buildings. So natural insulation materials are derived from renewable, biodegradable, or minimally processed sources, making them more environmentally friendly than its synthetic alternatives. They offer natural vapor permeability and breathability, and allow humidity levels to be better managed to ensure ongoing comfort and product durability. So you can see a few examples here. Sheep's wool, wood fiber, and hemp are probably the most common natural products used in construction. And you can see on the right hand side there, they're quite comparable to the mineral wool alternatives that we previously discussed. So you're looking at conductivities there of around 0.035 to 0.04. So again, these products are comparable to the synthetic products made by in the manufacturing process. These are usually, however, slightly more expensive, so around 15 to 25 pounds per meter squared, and this is usually because of demand for these products. There's obviously not as much supply for these products, so they're in higher demand. But again, it is a product that lends itself to historical homes and conservation areas, particularly if you've got timber construction as well. And here are just some examples of these products in retrofit, so you can see how durable they are. They can be used in external walls. Again, you can see an example here in the roof, and there's another example here on a suspended timber floor. So I think this was some wood fiber insulation, and these products lend themselves to, like I say, timber construction. Roof insulation. So again, one of the most common popular energy efficient measures. There isn't much to say about roof insulation in general, but there's usually two types. It'll either be mineral wool, so made by spinning or drawing molten mineral rock materials, These have a moderate cost, and they can also provide sound insulation as well as heat. And again, those conductivities there are around 0.032 to 0.044. So depending on what U value you're trying to achieve, you can specify products within this range. And again, they can be used in both loft insulation and in warm roofs if they're insulated between the rafters. And likewise, the alternative is fiberglass. So these are highly durable due to its corrosion resistance, and they're typically made of small flexes of molten glass. Again, similar performances to mineral wool, conductivity of around 0.03 to 0.044, and those typical costs are between 5 to 10 meters squared, £10 per meter squared. So these are the most common materials. As I said, there's not much to add in terms of that. In terms of roof insulation, it's pretty straightforward. But yeah, these products are often the most common products, and you can see here an example of what we tend to see in a typical retrofit. So new build homes, you're looking at around 400 mil of mineral wool to hit minimum requirements, but in a retrofit, that's maybe not always necessary. So insulation of fiberglass or mineral wool will usually be around 270 millimeters. So you can see on the image here, usually the first 100 millimeters is installed between the ceiling joists, and then it's cross-laid above another layer of insulation to provide that total thickness of 270 millimeters. One of the key considerations, however, is to ensure that any loft space does still remain well ventilated in order to reduce moisture buildup. Because if that occurs, then obviously the condensation and damage can occur and damage the roof trusses. So careful consideration around the eaves detailing when installing this product is key. But as I mentioned before, this is possibly the cheapest and most effective insulation measure that people can do in their homes, which is unsurprising why it is the most popular measure installed as well. Floor insulation. Okay, so this scenario it's not common that we see homes adapt floor insulation purely because of the impact that this can have on the occupants, but there is scenarios where you can retrofit floor insulation into an existing home. So it'll either be on a suspended timber floor. So you can see the example on the right hand here. We've got what would have been an uninsulated timber floor, and then you'll put in it can be various different products. It can be mineral wool, it could be PIR boards, it could be EPS, or again you could use some of those eco-friendly alternatives like wood fiber and hemp, but they can effectively be cut into shape and fit between the floor joists, and then usually there'll be a netting or a membrane below to ensure that insulation is tightly fitted. And then if it isn't going to be a suspended timber floor, it's likely to be a slab on ground floor. This is less likely as a scenario simply because most floor to ceiling heights will be, let's say, 2.4 meters. So in order to insulate a concrete slab, you would have to insulate above the slab or create a timber floating floor or something like this. So it's less likely to happen in retrofit purely because of floor to ceiling heights and the impact it'll have on the occupants in terms of having to remove all of the furniture. You'll have to remove the skirting boards, you'll have to remove plug sockets and change the heights of these things like that. So it's quite a significant uplift to upgrade floors in retrofit. However, there are examples that, and typically, if it is the case, then there'll be these sort of methods that will be adopted. But another key thing to consider when looking at retrofit and insulation is also thermal bridging. So U values tend to account for other fabric elements such as walls, roofs, doors, windows, account for around 70% of heat loss of a typical building, with the remaining 30% coming from thermal bridges in construction. Which is often either called a thermal bridge or cold bridging. And in retrofit, this refers to areas in a building where heat escapes more easily due to a break or weakness in the insulation layer. And these bridges allow cold to penetrate into the building fabric. So you can see on the right hand side here, we've got an image of a home that's had a thermographic survey, and you can see the eaves detail there. There's quite a lot of heat loss coming through the eaves and around the windows, window sills and the window jambs. You can see that sort of blue colour there identifying heat loss through the construction and also around the ground floor perimeter. So you can see that the warmer colour is the wall itself. So those will be well insulated, but then those thermal bridges are key to consider in retrofit. So it's important to, yes, make sure that the main elements are insulated, but really focus on those finer details at the end to make sure you don't exacerbate and increase heat loss at these junctions due to creating a sort of new path of least resistance in the construction line, in the installation line. So we've got some examples here of good practice in retrofit in terms of reducing cold bridging. So you can see the image here on the left-hand side. That is a plan view of a window detail, and you can see this wall particularly has internal wall insulation, and rather than just stop at the window reveal, you continue that insulation around the reveal and abut it against the window frame. So that's a really good way of continuing that insulation line right to the weak point, which will have been that junction between the window and the wall. And you can see here they've used a vapor permeable material to stop air entering the building fabric, but also allow moisture within the wall to safely escape. So on the right hand side, we have a ground floor wall construction. So again, this is another example of internal wall insulation and a suspended timber floor. And rather than just insulate the wall and insulate the floor, there's that key insulation edge detail. Sometimes that can be missed in retrofit, which had that not been there, that can obviously cause a significant cold bridge, which then you might have a buildup of condensation and mold growth on that corner construction, purely because that little bit of insulation edge detail isn't installed. So that little bit of insulation edge detail there kind of wraps that whole junction in insulation, which is a really good way of reducing cold bridging. So a really important thing to consider when developing your strategies in terms of insulation and specifications. A few more examples here. So we've got some external wall examples. So we've got a window head detail here. So again, like that previous example of a window detail, we've got the insulation just returning and abutting the window frame again, just to reduce that heat loss at the junction. Again, at the eaves detail, we've got that continuation of insulation around the wall, and where the wall and roof meet together, that insulation in that gap there that's labeled as 1 on that particular image. But obviously in that scenario, you can see above that insulation, there is around a 50 mil air gap to ensure that ventilation is continued through that roof, to ensure that the timbers don't rot due to poor ventilation rates. We've got a gable wall detail on the next image there. So again, you can see how there's insulation pushed up right against the wall. So you've got some internal, you've got 2 layers of roof insulation, and then that final perimeter insulation, just to make sure that, again, that continuation of insulation right up to the wall. And I've got some more examples there of a ground floor junction. Again, that perimeter insulation, this time installed below the finished floor, and again, just continuing that insulation to make sure that it doesn't abut the original block work. And then we've also got some examples there of a warm roof scenario. So we've got maybe a room in roof scenario, and again, just that insulation continues around. So you've got that continuation of insulation to ensure that the cold bridging is reduced to a minimum. So it's something you really need to consider during that design stage with your retrofit coordinators, to make sure that these sort of things are considered. Because as I say, it's around 30% of the overall heat loss is from these sort of junctions, so these key detail areas. So ventilation and air tightness. So why do we need ventilation? So older homes often had inbuilt natural ventilation, so that would be from open fireplaces and door undercuts, whereas new homes or retrofitted homes are more airtight and require ventilation strategy. So if you're going to add insulation, like if you add an internal wall insulation to your existing property, the chances are you're going to make it a lot more airtight than it previously was. So in that case, in order to make sure you don't create a new problem, it's important to address that ventilation issue and look at these two things in tandem. So ventilation can also provide fresh air for residents and prevents a buildup of moisture, CO2 and VOCs. And also, if you're receiving funding, government funding, it is obviously a requirement to ensure that the ventilation is not seen as an optional extra, and all homes are required to be adequately ventilated. There is a common phrase that people use, which is build tight, ventilate right. So obviously that is something that we should consider. And if you are going to put ventilation in, you need to make sure that it is appropriate for that particular dwelling. So why is ventilation air tightness important? Poor ventilation can often lead to condensation and mold growth and dampen the home, which can impact an occupant's health. Air tightness testing can help identify areas of air leakage, and this can be used to identify any repairs that are needed. And post retrofit, these these air tightness tests can help verify that the appropriate ventilation system have been installed for that particular property. Poor ventilation can also increase energy consumption as occupants use purge ventilation, so effectively just opening the windows to improve indoor air quality, which is it is fine to do that. Sometimes you have to do that. but it might be the case that poor indoor air quality is simply because there is not appropriate ventilation within that property. So we obviously want to try and avoid people having the need to open the windows all the time and release all that heat that's built up in the building as well. So we want to try and reduce that. There are various types of mechanical ventilation. We're going to go through those today. So we're going to look at intermittent extract ventilation, and then we'll look at passive stack ventilation, and then a more common mechanical extract ventilation. This can be either decentralized or centralized. And then we'll also touch briefly on mechanical ventilation with heat recovery. So intermittent extract fans, they're a good option for leaky homes as it relies on background ventilation by droughts. If there is ventilation, if there are fans installed in homes, they typically will be an intermittent fan like this. And cross ventilation tends to only occur between rooms by door undercuts and trickle vents. And these will be usually located in wet rooms, utility rooms, kitchens, things like that. And typically they'll either have a humidistat or they'll be connected to the light switch or something like that. So they turn on, there's a 5-minute overrun whilst you're using the toilet or you're using the kitchen or utility room, there'll be a 5-minute overrun, and after that, they switch off. They're okay, and they do provide obviously a level of ventilation, and can help reduce that moisture buildup post having a shower and things like that. But they are only ever on during that particular time, so it's not always the most effective way of improving ventilation and indoor air quality. Then we have passive stack ventilation. It's not too common in my experience, something that people use as an option, but this is effectively this extracts from wet rooms and are ducted up to the roof ridge, and this heavily relies on pressure differentials between the top and the bottom of the home, and intakes are typically trickle vents in the windows, and cross ventilation between rooms via door undercuts. So you can see there on the image on the right hand side, you've got that ducting from the kitchen, from the bathroom, and that pressure difference is adding that warm air up through the ducting and extracted through the roof, and then that pressure difference pulls that cold fresh air through the trickle vent. So it is a technology that's been around for quite some time. It's not something that I see people actively implement in their homes, but it is one of the options. And if you do see it, then this tends to be what it will look like on the right hand side. And then a more common example is mechanical extract ventilation, and this will be either a centralized system, which is shown on the image on the right hand side here, or it'll be a decentralized system, so there'll be one fan in each wet room. They kind of look very similar to intermittent fans, but they're just running continuously all the time, 24/7. And these can tend to be used on more airtight homes, typically with an air permeability of 3 to 5. I'll go into a bit more detail about what that is later on. But these sort of products are the most common we see installed in retrofits, typically just because they can be installed in each utility room, the WC kitchens, and they run continuously and provide that constant extract. So that is by far the most common. When it's centralized, it'll be like that in the corner there. So it'll be a centralized fan, but again, there'll be ducting going from each wet room and extracting that ducting from each wet room, and then pulled cool, fresh air through the trickle vents and door undercuts. And then finally, the most significant and most energy efficient form of ventilation is one combined with heat recovery. This requires very good air tightness results. And again, these operate similar to DMEVs in the sense that they run 24/7. You'll have a single point of intake with heat directly exchanged from the air and extract and supplied to all habitable rooms via a heat exchanger. And MVHR systems recover up to about 90% of heat from extracted air. It's not common we see these in retrofit simply because they do require ducting throughout, supplying it all into all living spaces, so lounges, bedrooms, and extracting from bathrooms, kitchens, utilities. So that does require quite an uphaul and pulling down ceilings and ceiling voids and making false ceilings and things like that in order to install them. There are other examples of products that can be used that don't require a central unit, but again, I've not seen them installed in my own experience. But yeah, an MVHR is a product that's quite common in new builds now, and effectively, yeah, it just extracts that warm, moist air from kitchens and bathrooms, and then sends it to this circulation fan, which you can see on the top image there, and then preheats any cool, fresh air that is being supplied into the bedrooms and lounges, and that can be used to help reduce the heating demand and provide that free supply of cheap, warm heating. And here's a little comparison of the three products here. So the initial cost of an intermittent fan around 15 to 50 pounds, so really cheap to install. A typical DMEV, you're talking around 75 to 150 pounds. And again, and the running costs of these products. So a DMEV, you're looking at a running cost of around 7 to 11 pounds per year for ventilation in all your different wet rooms for 24 hours a day. And these systems have very low running costs. So even in MVHR, you can see there an MVHR has £30 per year. But the installation costs of an MVHR are significant, between around £3,000 to £10,000, depending on the size of the property. So quite a significant variety in costs here. Heat efficiency of intermittent fans and DMEVs, you don't have a heat efficiency because it's not recovering that heat. They're not designed that they are just extract only. Whereas obviously an MVHR have excellent heat efficiency and they extract that stale air to the fresh incoming air. So there are strengths and weaknesses to all three, and as I said, the most common that we see is those decentralized mechanical extract fans, simply because they're relatively cheap to install, relatively cheap to run, and they work well at extracting from those wet rooms. Air tightness needs in retrofit programs. So most people, if they are going for a retrofit program, they will be under the past 25 requirements. So air tightness focus. So before we go into a bit more detail about that, we'll just go into a bit of detail about what air tightness is. So air tightness essentially focuses on the elimination of gaps and cracks on the external envelope of the building. It can help improve air tightness. Improving air tightness policies creates a more comfortable and energy efficient living environment. And air leakage can usually account for up to 50% of heat loss within the fabric. So it is really important to obviously bring that down. So improving air tightness can also help reduce that air leakage. Why do we need air tightness? So it's quite self-explanatory, energy efficiency. So it can reduce heat loss in the winter, and it can provide more occupant comfort and improve indoor air quality. So you can see on the right hand here, there's lots of examples of heat loss through construction. So through the roof, through gaps in downlights, through the top plates and ridges and things like that. There's a lot of heat loss through the ceiling. And then there's plenty of examples of where cold air can enter a property in drafts. So it can be through floor plates, it can be through designed ventilation through trickle vents, but there's obviously plenty of examples where it's not designed and it finds its way in through various cracks and gaps within the construction. So the best way to identify these areas is by completing an air tightness test. Now, a lot of people are probably quite aware of this process now. It's been around for quite some time. I think it was first introduced around the early 2000s. And it's a simple test in the sense that you put a large blower door fan on a door, and it looks like that image on the right hand side there. You can see that sort of red door with a fan. You'll either pressurize or depressurize the household. And from this test, you will be able to identify where those key gaps are within your construction. And you can sometimes add extra bits of kit, such as smoke guns and smoke machines, which can help show where the smoke is going, and it can show you where those key gaps are. Most key gaps are around penetrations from surfaces, so it could be boiler flues, it could be around the extract fans, it can be poor detailing around a windowsill, it can be around skirting boards and things like that. So this technology is quite good at identifying those key areas, and then from the back of such an assessment, you will be able to determine, by assessing the air permeability, what ventilation is required, or if you have post retrofit installed appropriate ventilation for that particular dwelling. And as I said here, there's a few more examples of ways of measuring air tightness testing. So there's the blower door example that I've just described there, and then we've also got the pulse testing method, which uses compressed air and measures pressure differences. You can't typically fault find with that particular technology. It's great at finding the air permeability, but if you are trying to look at gaps within your construction and identify if there's any leakages within your insulation line and things like that, that particular method won't be used. The blower door will be used in that respect, but you can also combine Air tightness testing with infrared thermal imaging. So that'll help highlight any cold bridges, as we mentioned before, in terms of that detailing around the eaves, detailing around the gable. Is there a consistent insulation line within the wall, within the roof? So thermographic cameras are great to use for both. During an air tightness test, you can really see those particular issues. It really highlights and exacerbates those cold bridges in construction. And I mentioned there before, you can also use tracer gas testing and smoke testing, which is just another way of showing where those leakages might be within your envelope. So these tools are available and have been available for quite some time. It's not mandatory in PAS 2035, but it is recommended because it gives you a great opportunity to understand where are the gaps in that construction, what technology is available. We want to put a DMEV fan in our rooms. What is our air tightness result? If it's then below 3, an air permeability of 3, then that DMEV probably isn't going to provide sufficient ventilation. So it's a really good opportunity just to verify that you've got appropriate ventilation installed in your properties. So yeah, it is recommended. It's only mandatory for, I believe, risk level C in PAS 2035. So any homes that are sort of heritage homes or anything like that, or high-rise flats, I believe. When to undergo an air test, so as I've just mentioned there, you don't have to, it's not mandatory, these air tightness tests are required, but they provide a great opportunity. And I could recommend using them before finishing touches like flooring is laid and furniture is installed, after all penetrations to walls and floors are made and sealed. So again, that's a really good opportunity to test those seals. Have they been sealed properly around the back of the toilets, around the fans, around boiler flues? It's a really good opportunity just to verify and check that those products have been installed appropriately. And again, if you've got that insulation, you put up interior wall insulation and you want to test that insulation line, are there gaps within the construction? Have we taped the insulation appropriately? Ground floor insulation, ground floors, timber suspended floors are usually very, very leaky. If you install those timber battens and put insulation in between, you can make sure that there's no air gaps within that particular construction. It's nice and airtight, and an air membrane that you've probably installed as well has been installed properly. So it's a good opportunity to verify that these products have been installed in line with the requirements. And as I mentioned before, it's a really good opportunity after the building's been constructed to complete an air test just to verify that the appropriate ventilation is installed. PAS ventilation requirements. So for every dwelling proposed for improvement, the retrofit designer shall use the information provided by the retrofit assessor to assess the adequacy of existing ventilation. So yeah, it is an essential requirement to review ventilation in PAS 2035. And you need to verify that it's acceptable and complete ventilation system. And of course, no evidence of condensation or mold growth can be present to pass requirements. Okay, that's me.